Alright, so first let's talk about the internal application of hash map. So a hash table, also known as a hash map, is a data structure that implements the associative array abstract data type, which allows keys to be mapped to values. So a key could be something like a name or string, and the value could be something like a phone number or some sort of data. So we could basically create a hash table to store a bunch of people's phone numbers. A hash table employs a hash function to generate an index, usually referred to as a hash code, into an array of buckets or slots from which necessary data can be retrieved. So to know more about hash function, let's move forward to the next slide. Hashing algorithm, or also known as hash function, is the calculation applied to a key to transform it into a relatively small index that corresponds to a position in the hash table. For numeric keys, divide the key by the number of available addresses and take the remainder. Address is equal to key and use the modulus operator, while n is the number of available addresses. And as you have seen, for alphanumeric keys, divide the sum of ASCII codes in a key by the number of available addresses and take the remainder. And lastly, following method is the one that divides key into equal parts and then adds the parts together, just like this one. So when choosing or writing a hash function, there are some objectives to bear in mind. First, it should minimize collisions, so less time is spent on collision resolution, and ultimately data retrieval will be quicker. Ideally, it should give you a uniform distribution of hash values, and therefore, the data will be spread across the hash table as uniformly as possible. And lastly, the hash function should be easy to calculate, and resolve should include a suitable method of resolving any collisions that do occur. So next is the key statistics. A critical statistic for a hash table is the load factor, defined as load factor is equal to n over k, where n is the number of entries occupied in the hash table, where k is the amount of buckets or size of the array. And take note that the amount of buckets must be greater than the number of entries. And also, load factor must be less than 1. So when load factor is greater than 1, you must increase the number of buckets by rehashing and modifying the hash function. So summing up, hash function is the core of implementing a hash map. It takes in the key and translates it to the index of a bucket in the bucket list. Ideal hashing should produce a different index for each key. However, collision can occur if two keys map to the same slot in the hash table. So the two common methods for collision resolution are separate chaining and open addressing. Resolving a collision by placing an item somewhere other than its calculated address is called open addressing, because every location is open to any item. Open addressing, all entry records are stored in the bucket array itself. When a new entry has to be inserted, the buckets are examined, starting with a hash to slot and proceeding in some probe sequence until an unoccupied slot is found. So, open addressing can use a variety of techniques to decide where to place an item that doesn't go where it should. This particular open addressing technique is called linear probing. If the calculated address is occupied, then a linear search is used to find the next available slot. For instance, we have here a specified hash table. So there are 5 keys to be inserted in the buckets. We have here John, Lisa, Sam, Sandra, and Ted. So first, in order for us to get the index of these keys, we're going to use hashing algorithms. So as you can see here, ang computed index ni John Smith ay 152. So dyan sa pupuntas. While si Lisa ay nasa index 1 naman. Sam, nasa 254. Sandra D, dito na magkaka-collision because they have the same index. with John Smith. So mangyari dyan is a linear search will be performed to find the next available slot. So since it's already occupied by John Smith, mapupunta to si Sandra D dun sa next slot, which is unoccupied yet. Okay, so next, Ted Baker. Ang computed index niya is 153, but then it is already occupied by Sandra D. So what will happen is a linear search will be performed to find the next available slot. So when resolving collisions, if the calculated address is occupied, linear probing involves trying the next place along it if necessary, the next and so on, until an empty slot is eventually found. But this can result in what is known as primary clustering. In other words, keys might bunch together inside the array while large proportion of it remains unoccupied. So there are, however, alternatives to linear probing that can help to avoid clustering. Rather than simply scanning along for the next available slot, every third slot along until the free space is found, the so-called +3 rehash. Talking about quadratic probing operates by taking the original hash index and adding successive values of an arbitrary quadratic polynomial until an open slot is found. Basically, quadratic probing will square the number of failed attempts. While double hashing applies a second hash function to the key when collision occurs, and the result of the second hash function gives the number of positions along from the point of the original collision to try next. So another way to deal with collision is known as chaining. In chaining, we use a linked list to manage collision. Elements that hash to the same slot are placed in a linked list, and the slot in the hash table would contain a pointer to the head of this hash table. For instance, this example is the example that we had earlier, right? Okay, so we have here another specified hash table. We have John, Lisa, Sam, Sandra, and Ted. So let's move forward to the scenario kung saan nagkaroon na ng collision. Alright? So John Smith and Sandra D has the same value of index. So what will happen here is John Smith will perform a linked list because siya yung nauna, and to be followed by Sandra D will also perform a linked list using pointer, no? Which is, mas maganda dito is same slot na sila. Di kagaya sa linear probing is that marami pang some sort of clustering, no? So with the chaining method, you can see that there are a greater proportion of items in the correct place, so the lookup is quicker than if you had used linear probing. Of course, traversing a linked list also comes at some cost. If the load factor is low, it may actually be more efficient to use open addressing. So take note of that. Our next topic is the implementation of hashmap in Python.
Hello everybody, welcome to the channel. It's W3 here. In today's Python tutorial video, we're going to be looking at a hash table or hash map. We're also going to be implementing our own dictionary in Python. So if you haven't already, hit that subscribe button for more great content and great tutorials in the future. Right, so a dictionary is an associative array, also known as hashes. Any key of the dictionary is associated or mapped to a value. The values of a dictionary can be any Python data, so dictionaries are unordered key value pairs. Dictionaries also belong to the built-in mapping type. So this is what we're going to be learning today, and this is also what we're going to be creating today in Python. So first we need to create our class, which is going to be called hash table. So class hash table. We then need to create our init method, so def underscore underscore init underscore underscore, and then self, which is referring to the instance or the object of this class. We then need a hash table size, so we're going to do self.size equals, and we're going to put 10 just for now, just so I can show you quickly what the hash table will look like. But in future, afterwards, we're going to put it at 256 later on, as that is sort of the default size for a dictionary in Python, so we may as well use it. And then we're also going to put self.hashMap, which is going to be a hash map, and that's going to equal square brackets and then a list for underscore in range, and then we're going to do 0 to self.size. So our hash map is basically a list that is full of lists, and that'll become more apparent as we go through the code. And we're going to just print self.hashMap just to show you. So I'm going to do h equals hash table. I'm going to run the code, and there we go. We've got a hash map here, which is all these lists inside one big list. And these lists here, these are slots or buckets, as some people call them, but I like to call them slots. And these are going to keep our key and value pairs. So yeah, and it's going to be no different to what we're creating. It's going to be no different to doing d equals dict in the end. Alright, so we're going to have to start off by creating the hashing function, which is going to hash our key. So we'll start off by doing def and then hashing underscore func with the parameter self and the key that is going to be hashing. So now we're going to call it hashed underscore key equals, and we're going to be using Python's built-in hashing function. So hash and then our key. That will hash our string, our key, whatever, into say like a 5-digit number, and then we modulate it, so divide it by self.size, and then whatever number's left over, which will be between 0 and the size of our hash map. So in this case, self.size equals 10, but we'll change that later on. So yeah, and then we're just going to return the hashed underscore key. So we're just returning it, and that's our hashing function done. So now we need to create the set function, and what that's going to do is it's going to set or add the item to the hash map or to our dictionary. So we need to begin by doing def set and then self and then the key and the value that we want to set, and then we need to do hash underscore key equals self dot hashing underscore func and then the key. So hash underscore key now is a number, it's an integer, and it's going to be between 0 and the size of the hash map because of this function here, and it's returning the hash key. Then we also need to do key underscore exists equals false, and then we got our slots. So slot, or what some people call a bucket, but I like to call slot equals self dot hash map square bracket hash underscore key. And that's no different to when you've got a list and then you use a square bracket, you put a number in there or integer, and that finds the position or the index of whatever you're looking at in your list. And I'll show you what a slot is right now quickly. A slot in our hash table or hash map, we'll get rid of that and run it. So these lists here, these are slots, and these slots are inside obviously this one big list, this list here. All these individual lists, these are slots, and they're going to be holding our items in our hash map or our dictionary. Alright, so let's move on. Next we need to do for item kv in enumerate and then the slot, and I'll explain that to you now. So the reason we're doing for I, kv in enumerate slot is because each slot can have more than one key and value tuple pair, and that's because of hashing collision. And to get around hashing collision, we're going to be doing chaining. So that means for each item in the slot there can be many more items, so we're going to have to iterate through them, as you can see in the picture here. To make it a little bit more simple, I'll create the pictures, and that's what we're going to be doing. So next we need to do this, k, v equals kv, and that's because kv has two items, a key and a value. It's going to be in a tuple, so we're splitting that up into obviously K for key and V for value. And then if key is equal to K, key underscore exists is equal to true, and we're just going to break. And then we need to do if key underscore exists, and just a little tip here for you guys, we can do if key underscore exists instead of doing equal to true, because key underscore exists is true, so it's no different saying if true. It's no different saying if key underscore exists is equal to true, basically. And then we're going to do slot, square bracket, I, index in the slot, and then that equals our tuple and our key and value pairs. And then we can do else slot dot append and a tuple and then key value. And that's our set function done. So now it's time to do our get function, and that's going to be to get the using the key, get the value from the dictionary or a hash map, etc. So start off by doing def get and then self, and then the key that we'll be using to obviously get our item. And then we need to do same as we did for set. We're going to need to do hash underscore key. We need a hash key, and we're going to need a slot. So hash underscore key equals self dot hashing func, and then the key. And then we also need a slot, which is going to equal self dot hash map square brackets and hash underscore key, just like before. And then for kv in slot, and then same as before, k comma v equals kv. And then if key is equal to k, if it's found the key, we can just return v, return the value basically. And also we can do else, if the key is not there, basically it's not found, we can raise a key error. So raise key error, and we can just put does not exist, and that's our get function done. So now that we've done this bit, let's just go over the code, see if there's any mistakes or anything. Right, this here, print self hash map, we can comment that out because we don't need to do that anymore. And also, if key underscore exists, it's not exists, it exists. Yep, that should be fine. Now we're going to create our instance or object of the hash map or the dictionary. So h equals hash table to instantiate it, and then we're going to do h dot set and then key 1 and value 1, and we'll create two more of these, key 2 and 3 here, and value 2 and value 3. So we've set it, and then we're going to print h dot hash map, and as you can see, we've got key 1 and value 1, key 2 value 2, key 3 value 3. Great. And now I'm going to show you about collisions and how we've overcome that by doing chaining. So if I set this to 10 and that to 20, that's because when those values are hashed and then divided, and the remainder, because they're the same, they're both a multiple of 10, they should be in the same slot. So we'll test that out, and here we are. We've got this list here with a tuple of 10 and value 1, comma, and another tuple 20 value 2, and they're in the same slot or list. So yeah, we've chained our items, which is good. Now you're probably thinking, well, yeah, that's kind of like a hash map or dictionary in Python. Oh wait, we've got to do get as well. h.get, and we'll just do 10, and we've got a print, and yeah, value 1. So get works as well. But you're probably thinking right now, in Python we use square brackets. We don't use get or set. We don't use the functions like that, and that's right. So we're also going to be creating, we're going to write a bit more code so that we can use brackets to add or set the key and values to our dictionary or hash map, and also print and get the values. So we can just delete this quickly. It's very simple to get it like Python does it. We're going to do def underscore underscore and then set item underscore underscore self and then the key and the value. Now underscore underscore set item underscore underscore, that's a Python magic method. That's something Python has implemented. That's part of the Python architecture. We can't actually recreate that ourselves, but I've tried, don't you worry. But yep, that's what it is, and it's very simple. We'll just return self dot set key and value, and then the same for get. We're going to do def underscore underscore get underscore get item underscore underscore and then self and then key, and we're going to also return self dot get key. Before we run the code, we need to come up to get. No, we don't actually. Yep, we can just run this code now. So we're going to do h equals our hash table, which is no different to doing that in Python. We've created our own, and then we're going to do h square bracket key 1 equals value 1, and then we're going to print h key 1, and let's see if that works. And yep, we've got value 1 because we've set the key 1 to value 1 there, and then we're printing it from the hash table, which is our dictionary, and we've got value 1, and there we have it. We've created our hash table and dictionary.